Today we're going to be looking at the first day of Module 7, which is going to be all about circles. So starting off with circles, we're going to first look at all of the different angle relationships that we have whenever we've got different angles drawn within the circle. So you may want to pause the video here and write down some of the key vocabulary that we're going to use throughout today and the rest of this unit. So a central angle is an angle whose vertex is at the center of the circle. So that's the key component, that our vertex is at the center. A semicircle is half of a circle, and since we know that a full circle is 360 degrees, a semicircle is 180 degrees. A minor arc is a part of the circle that's smaller than a semicircle. So for example, if we've got a circle and we've got just this tiny little curvature here of that complete edge of the circle, we call that an arc. So if we had 2 points here, let's say they were A and B, to name that arc, we name it by its endpoints, and we put a curvature symbol above to show that this is part of the circle, which, like I said, we're going to refer to as an arc. A major circle is larger than a semicircle, and it's named by the endpoints and one other point on the arc. So in other words, we're going to need 3 letters to name this guy. So if we look at that same circle, and let's put point C here, if we're talking about from A all the way to C, our endpoints are A and C. But instead, if we just put AC, we take that shortest path. We take the minor arc that's shown there in blue. So if we want to follow the red arc, we've got to say go from A to C, but go through B first. Adjacent arcs are 2 arcs that are side by side. So in this particular picture, we could say arc ABC and as well as arc CA. Those are adjacent. They're right next to each other or have a common endpoint. And concentric circles are circles that have the same center. So we've got 1 circle, 2 circle, 3 circles. They all have that same center is what makes them concentric. So a really good example of that is if we think about dropping a pebble into water. We see those ripple effects that come out. Those are examples of concentric circles in the real world. Another kind of fun fact here, they say that if you have a headache, massaging your temples in concentric circles can help relieve that stress sometimes. So just a little fun fact today. So again, I'm going to try to zoom this out just a little bit because I know that's a little bit hard to see here. So a semicircle is half of the circle. A minor arc is less than half of the circle, and a major arc is more than half of the circle. So in blue here, we see that major arc SRT, or sorry, STR. This is a T here, that's really hard to see. So STR or RTS would be that major arc. The minor arc RS is shown in red. So what we're going to do first is just identify what we see. So a minor arc, one example of that would be arc AD, arc AC, CE, ED, and so on. We can list several of those here. To find your semicircles, you always want to look for your diameters. So I've got 1 diameter here from D to C. So 1 semicircle would be DAC, or I could say that in reverse, CAD. The one on the bottom of that, CED, is also a semicircle. And I have a diameter here, so I can say ACE. Again, you could reverse that order, that'd be totally fine. Or ADE. So to find your semicircles, the easiest way to do that is to find your diameters. Major arcs have to be bigger than half the circle, and it says we have to contain point A. So you could have lots of different answers here. As long as A is on that major arc, your answer is correct. So I could say from D all the way to E. Now notice when I'm going to name that, I'm going to say go from D towards A and end at E. We could have also named that DCE, but that A gives us a little bit more directional sense in terms of where we're going to go first. So we want to use the endpoints and one of the points along the path to name that. Again, guys, you could have lots of different answers here in terms of your major arcs. As long as they're bigger than half the circle and they contain point A, we're good to go. So practice down here at the bottom, name one of each. A minor arc is just anything that's less than half the circle. You could have a variation of answers here. A major arc is just bigger than half the circle. Again, you could have many different answers here. We just want to practice with those three letters. In our semicircles, we want to look for those diameters. We've got one here as well as one here. So depending on which one you chose to look at, we could say RST, we could say RQT, or we could look at the SU diameter and come up with several different answers as well. So now let's dig a little bit deeper into the actual angle relationships now that we know the key vocabulary. So again, a central angle has its vertex at the center of the circle. The measure of the central angle will always equal the measure of the arc. So if that x there is 40 degrees, then the arc measure here, this curvature, is also 40 out of the full 360 degrees. An inscribed angle has its vertex sitting on the circle, right? So here our vertex was at the center. Now our vertex is sitting on the circle. So whenever your vertex is on the circle, that angle is half the measure of the arc. So, for example, if I know, let's use our same number here, if I know that this arc is 40 degrees, then that angle is half of that, which means x is 20 degrees. So essentially, all that we're going to learn today about angles hinges on where is your vertex. So I would circle the fact that our vertex is at the center, and for this, our vertex is on the circle. That's what's going to key us off as to what to do. You'll notice here I've included a vocab word, the intercepted arc. If you think about an interception in football, that's when we catch the opposing team's ball. So an intercepted arc, we're catching this arc in between our hands, right? So we're catching that 40-degree angle. That is our intercepted arc. So let's put this into practice a little bit here. So we're going to find both the arc measures and some angle measures here. Everything here, it has a vertex at the center. So essentially whatever my central angles measure is the same as the arc. And everything I've learned up to this point still applies. So I know if this is 90 degrees and I have a flat line here, that this is also 90 degrees. And if I've got 151 there, I've got 29 left here. So I've found all of my central angles. And remember that our central angles are the same as the arc. So if that angle is 90 degrees, this arc is 90 degrees, this arc is 90 degrees, this arc is 29, and this arc is 151. Once I've got everything labeled, I can go back and answer their question. So they say the measure of the arc from G to J is 90 degrees. The measure of the arc from H to I is 29 degrees. From H to I to J, so we're going from here all the way around, that's 29 and 151 put together, which is the same as a semicircle, which is 180 degrees, and so on. So pause the video here, try the rest of these on your own, and then come back and check your answer. So for the number 7, G to J to I, I'm adding that 90 and the 151 together, so that's 241 degrees. From G to H to J, I'm adding the 90, the 29, and the 151 to give me 270. From G to J to H, 270 as well. From H to G to J, that's a 180. From G to H is a 90-degree arc. From G to H to I, now that is a minor arc, but they've chosen to use 3 letters, which they can do if they want. Or they could have just called that GI and we would have gotten the same answer. But 119 is our measure here. From H to J to I, That's almost the whole circle. It's everything but the 29 there, so I could also do 360 minus 29, or I could add all of that together to get 331. J to H to I, that's a 180 plus a 29, that's 209. And J to I to G is a 270. So again, because our vertex was at the center, the measure of the arc is the same as the angle. Now we're going to move our vertex. Notice this 50 degrees has its vertex sitting on the circle. So now we're talking about what we call an inscribed angle, meaning our vertex is sitting on the edge. And our angle is always half the measure of its intercepted arc. So 50 is half of 100. And if I look over here, 48 this time is labeling the actual arc measure. So remember, the angle is half the arc. So half of 48 is 24. Looking at what we have here, they want to know the measure of angle T. So that's that 24 degrees that we just found. And the measure of arc QR, we haven't found yet. So if I look, QR is here. That's what I'm looking for. But notice, you do have a diameter here. And our diameters are going to play a key role in being able to solve these circle questions. Because I know that all of that should be 180 degrees. So with that, if I know that this arc is 100, then I've got 80 degrees left over for QR. Notice how I highlighted that diameter. I made it stand out bold. I would recommend that anytime you see a diameter, you do that, because that'll always help you find those missing pieces. So let's practice a little bit here using our inscribed angles. Again, that means that our vertex is sitting on the circle. So whenever our vertex is on the edge of the circle, that angle is always half of the arc. So that's 45 degrees. In this case, we know the angle, so 38 is half of what? Or I can say 38 times 2, which is going to give me 76 degrees. For this next part, notice the angle in red is shown. That's what we're looking for. I know that this angle is 72, so the inscribed angle is half the arc. If I need to double that, 144 degrees. And I'm looking for angle X right here. So if I notice, that intercepts the same arc, which means I'm going to divide that 144 in half again, and I'm going to end up with 72 degrees. So that shows us that if two angles intercept the same arc, they're equal to each other. Two more questions down here. This is our angle sitting with its vertex on the edge of the circle. So remember that the angle equals half of its arc. So looking at that, 8x plus 10 should equal half of 12x plus 40. Distribute 6x plus 20, and then solve like we always would. I end up with an x value of 5. From here, we're trying to find A and B. So remember, we still know that all the way around is a full 360 degrees. So if I take 360 minus 60 minus 82, I know that this arc, arc A, is 218 degrees. And this angle, whose vertex is sitting on the circle, is always half of that arc. So if I take half of that, B is 109. Again, guys, our measures here are all hinging on where is our vertex. So next we're going to talk about an inscribed polygon and a circumscribed circle. So inscribed, think of that as inside, meaning we have a figure who is perfectly inside a circle, meaning all of its vertices will lie on the edge of that figure or that circle. So they've got both an inscribed triangle and an inscribed quadrilateral shown for you here. And a circumscribed circle is the circle that surrounds that figure. So circumscribed means we're going around the outside. Inscribed is what is actually inside the figure. Now, when we have a quadrilateral that is perfectly inscribed in a circle, the opposite angles are always supplementary. And that's going to be something you're going to want to write down in your notes. But whenever a quadrilateral is inscribed in a circle, its opposite angles are always supplementary. So if I notice, I've got all 4 vertices lying on the circle. So this is an inscribed quadrilateral, which means x should be whatever it adds up to with 80, the one across from it, to get 180. So that means that x is 100 degrees, and y is across from 75, so 180 minus 75 leaves me with 105 for y. For this next picture, those two a's added together would have to equal 180. So that tells me that a is 45, and my 4b and 2b would have to equal 180, which means b is 30. There are 2 other examples at the bottom. For sake of time, I'm going to move forward, but you're welcome to try those on your own. For this last little bit here, we're going to kind of put together everything that we know about these inscribed angles. So if I look at this, I know that 108 is this arc in between the arms of angle A. And since my vertex is sitting on the circle, that tells me that that angle is half of that arc. So A is 54 degrees. B has its vertex sitting on the circle as well, and it opens up to the intercepted arc of 60. So B is 30 degrees. And then if I look at that, I've got 54 and 30 that are representing these 2 angles right here inside of that triangle. So if I do 180 minus the 2 that I've already found, I should be able to find angle C. So C should be 96 degrees. The next few questions are going to combine what we know about an inscribed quadrilateral as well as what we know about our inscribed angles. So angle A is across from 68. So remember, those opposite angles should add up to 180. So A is 112. And now that I know this angle, I've got 2 other unknowns. I've got B and C. This 112 has its vertex sitting on the edge of the circle. So that's that inscribed angle. So I should be able to take that 112 and double it to get the measure of this arc, which is 224. So from there to there is 224 degrees. I already know that part of that angle, or that arc rather, is 104. So B would be whatever 224 minus 104 is, which comes out to be 120. Alright, so we found our A value, we found our B value. I apologize for that interruption, but we are going to pick up here finding C. So looking at what we know so far, I also know that this inscribed angle is 71. So if I take that 71 and I double it to get the measure of the arc, I've got 142 degrees from here to here. And I already know that part of that is 104, so if I subtract what's left, I know my C value is 142. So now I've got all of the missing components of this picture. I would recommend that you try 11 on your own and then come back to check. So for 11, I need to find A, B, C, and D. C and D are going to be the quickest because all I have to do is subtract their opposite angle from 180. So C is going to be 84 degrees and D is going to be 80 degrees. And A and B are going to require a little bit more work. So if I look at what I have this angle, this 100 here that opens out, which tells me that all the way from here to here is a measure of 200 degrees. So if I've got 200 degrees and I've used up 99 of that. I've got 101 left for angle A. Now I'm going to erase those markings just so I've got a little bit more room here, but I'm going to put 101 degrees for my A value. So now that I know that, I can also open up this C angle here, which I already know is 84, and if I double that 84, I've got 168 degrees. I already know that A is 101, so if I take that out, I've got 67 degrees left. Down here on the last row, we've got 72 as this arc, that intercepted arc of X. So if the measure of the arc is 72, the angle is supposed to be half of that, so X should be 36. Y is also an angle that intercepts that 72 degrees, so Y is also 36. We're going to do 13 on your own, and then I would recommend that you try 14 and 15 on your own. So looking at 13, I've got this diameter here, which I know splits my triangle into two semicircles, or two 180s. So if I take 180 minus 95, I have 85 degrees for A. I also notice that angle B has its vertex sitting on the circle, and it opens up to an intercepted arc that's 95. And the angle is supposed to be half of that arc, so 47.5 degrees. Last but not least, angle C opens up to this entire semicircle. So half of a semicircle is 90 degrees. Again, I would try the last two on your own and then come back to check. And then we've got all of our questions answered in this section that deals with inscribed angles. So last but not least, we're going to throw in what happens if the angle is somewhere inside the circle but not at the center, or what happens if the angle has its vertex outside of the circle. So when the vertex is inside, it's half the sum of the arc. So we're going to find the intercepted arc here, and the vertical angles intercepted arc over here. We're going to add them together and then take half of that. So, for example, if I knew that this was 100 degrees and 60 degrees, then X would be half of 60 and 100 put together. So half of 160, which is going to leave us with 80 degrees. At the bottom, since the vertex is outside the circle, then we need half the difference of the intercepted arcs. So we've got one of them here and one of them here. So again, let's use those numbers just to make our lives a little bit easier. If we've got 160 as our two arcs, then X should equal half the difference of those numbers. So half of 40 would tell us that X is 20. We're going to do a couple of practice problems with this, and then we are almost done with our notes. Remember that everything we've learned today hinges on where is the vertex of this angle. So that's going to be the first question we ask each time. So our vertex here is inside the circle, but not necessarily at the center. So because of that, we're going to say the angle, or the measure of the angle, equals half the sum of the arcs. So X should equal half of 90 plus 46. So if I take half of 90 plus 46, I end up with X equals 68 degrees. For the next one, same thing, our vertex is inside the circle but not at the center. So X should equal half the sum of the two parts. So half of 116 plus 70 gives us an X value of 93 degrees. Now notice for this particular picture, I don't know this arc and this arc. So what I'm going to do instead is I'm going to place a Y value here, And if I can figure out what y is, x and y are a linear pair, so I can just subtract from 180 to figure out my final answer. So y has its vertex inside the circle, so it's still half the sum of the two arcs. So half of 28 and 20. Half of 48 is 24. So I now know that that y that I added to the picture is 24. So 180 minus 24 tells me that x is 156 degrees. I'm going to use a similar method for this next one here. I'm going to do 180 minus 39, or 139 rather, and that's going to give me 41 degrees for this angle here. So remember, our formula is the angle equals half the sum of the arcs if our vertex is inside the circle. Since it is, 41 should equal half the sum of the two arcs, x and 40. To get rid of that 1/2, I'm going to multiply by 2 on both sides, so that 82 equals x plus 40, which means x is 42. If our vertex is outside, like it is here, then we're going to use the vertex outside formula, which says the measure of the angle is half the difference of the arcs. So the way I remember this is if the vertex is outside, I think about the phrase, it's out there, it's different, then that reminds me to take the difference of those two numbers. So in this case, our angle is 20, which should equal half of the larger arc minus the smaller arc. I'm going to multiply by 2 on both sides. I'm going to subtract that 95 from both sides. And I'm going to have negative 55 equal negative z. So z is regular old 55 degrees. Might not be a bad idea just to double check yourself. Is 90 minus 55 cut in half the same thing as 20? And if it's not, I know I've done something wrong. Our vertex is outside yet again, so the angle should equal half the difference. I would recommend that we do number 5 together and you try 6 on your own. Number 5 only gives us 240, but this other arc here should be the rest of that total 360 degrees. So I'm going to label that as 120. So when I take half of 240 minus 120, I find that x equals 60. Try the last one on your own and then come back to check. Again, we're going to use the fact that a full 360 is all the way around the circle, so subtracting the two arcs we already have tells me that this is 175. So my angle, since it has an external vertex outside of the circle, is half the difference of the two arcs, so 175 minus 65. Half of 175 minus 65 is 55 degrees. Guys, this is all we're going to cover today. I know that's a lot of content, but thank you so much for your participation. If you have any questions, feel free to let me know. If not, proceed to the practice. Have a great day.